Tonight, we are going to dismantle an image that has been sitting in your mind since childhood. A neat, beautiful, spiral galaxy, seen from above, glowing softly at its edges and brightening toward a warm, densely packed core. You have seen this image in textbooks. You have seen it on classroom walls. You may have even held it in your hands in the pages of a science magazine, one of those stunning photographs that made you feel small and full of wonder at the same time. And for most of us, that image has quietly served as our answer to one of the oldest questions a human being can ask while looking up at the night sky. What is at the center of all of this? What sits at the heart of the galaxy we live inside? The answer is not what you think it is. It is not a brighter cluster of stars. It is not a denser region of light. What sits at the center of the Milky Way is something that produces almost no visible light at all. Something you will never see with your naked eyes. Something that swallowed 4 million suns without leaving a single photon behind. And surrounding it in the few hundred light years closest to it is an environment so extreme, so violent, so paradoxical, that it breaks almost every rule we use to describe the rest of the universe. Young stars that should not exist. Ancient gas clouds drifting with the chemical building blocks of life. Invisible structures so enormous they dwarf the galaxy's own disk, ghostly and silent, tens of thousands of light years tall, inflated by something that happened millions of years ago and may happen again. Tonight, we travel to the center of everything we live inside. We will begin with the familiar image, the one you already carry. We will watch it crack, then break, then dissolve entirely until the original question itself, what sits at the center, turns out to have been the wrong question all along. Before we go any further, if this kind of slow, deep exploration is something you value, a like or a subscribe genuinely helps this channel reach more people who need it. It takes a second for you, and it makes a real difference. Now, let us begin. The first thing we need to do is take that comfortable picture out of your mind, hold it up to the light, and look very carefully at everything it gets wrong. Close your eyes for a moment. Actually close them if you can. And let the image come on its own. The image that every one of us carries, the image that floats up the moment someone says the words, our galaxy. What do you see? You probably see a spiral. A flat, elegant disk, wider than it is thick, with 2 or 4 great arms curling outward from a glowing center, the way cream curls in coffee if you've barely stirred it. The outer edges are dark, thin, almost translucent, but the center is bright. It is warm, amber-toned, dense with the accumulated light of countless stars packed tightly together, the way a city center glows brightest from an airplane at midnight. It is orderly. It is beautiful. It is, above all else, familiar. That image is in every textbook ever printed. And it is not a photograph. This is the first thing we need to understand, and it matters more than almost anything else we will discuss tonight. Every iconic image you have ever seen of the Milky Way from above, the flat spiral with its curling arms and its glowing core, is an artist's reconstruction. A calculated, informed, carefully assembled illustration, built from data, from observations of other galaxies, from mathematical models of how stars distribute themselves. It is our best guess about what our own galaxy would look like if we could somehow step outside of it, travel 2 million light years away, and turn around with a perfect camera. We have never done that. We cannot do that. We will never do that. We are inside the galaxy. We have always been inside it. Every measurement we have ever taken of the Milky Way has been made from a single vantage point roughly 26.0 light years from the center, sitting on a minor arm of a barred spiral galaxy. On a small rocky planet looking outward and inward, simultaneously trying to piece together the shape of a house while standing in one of its middle rooms. That is the honest situation we are in. And it is more humbling than most of us realize when we casually glance at that spiral diagram and nod as if we have understood something. Let that sit for just a moment. Now let us look at what we actually do know, because what we know is genuinely extraordinary, even before we get to the part that dismantles everything. The Milky Way is a barred spiral galaxy. It has a diameter of somewhere between 100,000 and 200,000 light-years, depending on how you measure its outermost tendrils, and it is home to somewhere between 100 billion and 400 billion stars. Those numbers are so large they stop feeling real almost immediately. So consider it this way. If every star in the Milky Way were a grain of sand, and you poured them all out onto a beach, you would need a beach several kilometers long and several meters deep to hold them all. Not the whole ocean, just a very large beach. Our sun is one grain on that beach. You are standing on a small pebble orbiting that grain. We sit on the Orion Spur, a modest segment between two of the galaxy's major arms, the Perseus arm and the Sagittarius arm, which is itself named for the direction we look when we look toward the galactic center. On a dark, clear night, far from city lights, you can see that center as a river of faint, milky light stretching across the sky, densest and broadest in the direction of the constellation Sagittarius, low on the horizon for those of us in the northern hemisphere on summer nights. Ancient peoples saw that band and called it by hundreds of names: a river, a road, a seam in the sky. They did not know, could not have known, that what they were looking at was the interior of a disk 100,000 light-years wide, seen edge-on from a point two-thirds of the way out from its center. We orbit the center of this disk. Our sun completes one full orbit approximately every 225 to 250 million years. This is sometimes called the cosmic year, or the galactic year, in the time it takes our solar system to make one complete circle around the galactic center. Entire geological epochs rise and fall on Earth. The last time our sun was in this exact position in its orbit, the first dinosaurs were only just beginning to walk the Earth. The time before that, our planet had not yet developed complex animal life. We are, in the most literal sense, passengers on a very slow carousel, and we have only ever been on one part of it. We have only ever seen one view, but let us go back to that glowing center in the familiar illustration. There is a reason the textbook image shows the center as bright and warm and inviting. It reflects something real. The central region of the Milky Way does contain a much higher density of stars than the outer regions. The galactic bulge, as astronomers call it, is a roughly spherical concentration of older, redder stars, hundreds of light-years thick, surrounding the true center. When you look at another spiral galaxy face-on, that bulge is exactly what produces that warm central glow. The image is not fabricated. It is not dishonest, but it is incomplete, profoundly, astonishingly incomplete. Because if you try to look at the center of the Milky Way, not in an illustration but in the actual sky with your own eyes or even with an ordinary optical telescope, you see almost nothing. Not brightness. Not a cluster of warm stars. You see darkness and dust, and the faint smear of a few distant stars half buried in murk, as if someone has drawn a curtain across the most important part of the view. The center of our galaxy is hidden. It has always been hidden from ordinary light. Between us and the galactic core lies an almost unimaginable quantity of dust and gas, the accumulated debris of stellar nurseries and stellar graveyards, ancient supernovae, molecular clouds so dense they block every photon of visible light trying to pass through them. It is as if the galaxy has built a wall around its own heart, and for most of human history, that wall was absolute. No telescope, no matter how large, no matter how carefully ground, could penetrate it. The center existed as a concept, a logical necessity implied by the spiral shape of the galaxy, but not as a place we had ever truly seen or measured. We inferred it. We pointed toward Sagittarius and said, somewhere in that direction, approximately there, the center must be. And then we waited for technology that could see in wavelengths the human eye was never designed for. There is something quietly extraordinary about this fact. We live inside a galaxy. We have lived inside this galaxy since before we were human. Every ancestor of yours, every creature that ever walked or swam or crawled on this planet, has spent their entire existence inside this vast structure. And yet the center of that structure, the gravitational heart of the entire thing, was utterly invisible to every one of them for the entirety of life's history on Earth. No light from the galactic center has ever reached a human eye directly. Think about that. No light, not dim light, not filtered, reddened, faded light. None. What we see in the direction of the center is the dust, and the scattered stars on this side of that dust, and the smear of background glow from billions of sources mixed together. But the center itself, the actual core, has always been behind a curtain, always concealed. And this means that the comfortable, bright, tidy image of a glowing galactic core that lives in your memory is not something anyone has observed. It is something we were handed. It was placed there by diagrams and illustrations and NASA artist renderings, repeated so many times in so many contexts that it hardened into something that felt like memory, like knowledge, like fact. But it was always, at least in part, a placeholder, a best approximation drawn over an absence. The real center waited behind the dust, and when we finally found a way through, what we found there was not what anyone expected. It did not glow the way the illustration promised. It did not resolve into a denser, warmer version of the rest of the galaxy. What was there, lurking at the very gravitational heart of the Milky Way, was something that the diagram, no matter how many times it was reprinted and distributed and hung on classroom walls across the world, had never once shown you. Something invisible, something ancient. Something that bends spacetime around itself like a fist closing around the fabric of reality. And the very first clue that it existed did not come from looking at the center at all. It came from watching the stars near the center move, and realizing, with a slow and deepening horror, that nothing visible could possibly be doing what was being done to them. So here is the question I want you to sit with as we move into what comes next. What could be so massive, so compact, so dense, that it pulls millions of solar masses worth of gravity from a point so small you could fit it inside our solar system, and yet produce almost no light at all? Because the answer, when we arrive at it, is going to be stranger and more beautiful than almost anything else we know about the universe. For most of human history, the center of the Milky Way was a question with no answer. Not because astronomers were not asking it. They were asking it constantly, urgently, with every instrument available to them. But the wall of dust between us and the galactic core blocked every attempt to see through it. Visible light, the spectrum our eyes were built for, the spectrum our telescopes were designed around for centuries, was useless. Absorbed, scattered, devoured by the dark molecular clouds lying between here and there like a drawn blind over a lit window. And so the center remained a hypothesis, a logical necessity, a place we could point to on a map but never visit, never even photograph. Then, in 1974, two astronomers changed everything, not by looking through the dust, but by listening through it. Bruce Ballack and Robert Brown, working with the National Radio Astronomy Observatory, detected an unusually bright, compact source of radio waves coming from the direction of the galactic center. Radio waves travel through dust the way sound travels through fog. They do not scatter. They are not absorbed. They pass through the curtain that stops visible light, as if the curtain simply is not there. And what Ballack and Brown heard in the radio data was something small and intensely bright, sitting in the exact geometric center of the galaxy, radiating energy at frequencies that did not match any ordinary object known at the time. They named the region Sagittarius A. The bright compact source at its heart they designated Sagittarius A, the asterisk borrowed from atomic physics notation, used to denote an object in an excited, energized state. Sagittarius A star, SGRA. They did not know what it was, not yet, but they had found it. For the next 2 decades, SGRA sat in the astronomical literature as an interesting anomaly. A bright radio source at the galactic center, probably associated with some large concentration of mass, but the details, the specifics, the true nature of the thing remained stubbornly out of reach. To understand it fully, you needed to be able to see the stars near it, to watch them move, to measure their velocities and trace their paths. And to do that, you needed to see through the dust. In the 1990s, that finally became possible. Infrared light, longer in wavelength than visible light, does not interact with dust grains the way shorter wavelengths do. It slips through. Not perfectly, not without some loss, but enough. When astronomers pointed newly developed infrared cameras on the world's largest telescopes, the Keck Observatory in Hawaii and the Very Large Telescope in Chile, toward the galactic center, the curtain did not drop entirely, but it thinned. And through the thinning, they began to see stars. Dense, fast-moving, tightly packed stars, swarming around a single dark point like sparks circling a drain. What they saw there stopped them cold. Stars near the galactic center were not moving the way stars are supposed to move. Stars in the outer regions of a galaxy drift in slow, enormous arcs, taking hundreds of millions of years to complete a single orbit, moving with the stately, unhurried patience of objects in a very weak gravitational field. But the stars near the galactic center were racing. Not drifting, racing. Moving at thousands of kilometers per second, carving tight, sharp ellipses in the infrared sky, their paths clearly curved, clearly bound, clearly orbiting something located at a single fixed point in space. That point produced no light anyone could detect. No visible glow, no infrared source, nothing that corresponded to any ordinary stellar object. And yet the stars were orbiting it, locked into its gravity, flung through their arcs by a force that had to be enormous, concentrated, and invisible. These stars became known as the S stars, S for Sagittarius. Dozens of them, cataloged and numbered and tracked with obsessive precision over years, then decades. Each one following its own individual path around the same central point, like planets around a hidden sun, except that these orbits were nothing like planetary orbits. They were wildly elliptical, radically tilted, inclined at all angles to one another, as if a handful of comets had been thrown into an enormous gravitational blender, and each one had settled into whatever path the mathematics of its initial trajectory allowed. One star in particular became the most important star in modern astrophysics. It is called S2. S2 is a blue main sequence star, roughly 15 times more massive than our Sun, burning hot and fast the way young, massive stars always do. There is nothing remarkable about it as a star. What is remarkable is where it lives and what it does. S2 orbits Sagittarius A with a period of just over 16 years. 16 years. Compared to our Sun's 225 million-year galactic orbit, 16 years is barely a breath. Jupiter takes 12 years to orbit the Sun, from an average distance of roughly 780 million kilometers. S2 takes only slightly longer than that to complete an orbit around the galactic center, but its orbit is not measured in millions of kilometers. Its semi-major axis spans roughly 970 astronomical units, and its closest approach to the central point, its periapsis, brings it within approximately 120 astronomical units, or 17 light hours, of whatever is hiding there. At periapsis, S2 moves at roughly 7,650 kilometers per second. That is approximately 55% of the speed of light. In more human terms, it is traveling at about 17 million miles per hour. If you placed S2 in our solar system and let it move at that speed, it would cross the entire diameter of Earth's orbit in under 3 minutes. This is not a gentle drift. This is not a leisurely arc. This is a star being hurled through space at a speed our intuitions have no framework to hold. And it does this not once, not twice, but over and over, completing its full 16-year orbit again and again, as it has presumably been doing for millions of years, drawn back each time by the gravity of something at the center of the loop. S2 is not alone. Another star, discovered in 2022 and designated S4716, completes its orbit in just 4 years. 4 years. It passes within roughly 100 astronomical units of the central point, less than 3 times the distance of Pluto from our Sun, and it survives. A full star, burning and intact, sweeping through one of the most extreme environments in the known galaxy on a schedule shorter than the time between U.S. presidential elections. Now, apply Kepler's third law. This is the mathematical relationship discovered by Johannes Kepler in the 17th century, refined by Newton, and used ever since to calculate masses from orbital mechanics. The principle is simple. The speed and period of an orbit tell you the mass of whatever sits at the center. The tighter and faster the orbit, the greater the central mass must be. When you run the numbers from S2, from S4716, from the dozens of other S-stars whose orbits have been traced with extraordinary precision over 30 years of infrared observation, the answer that comes back is always the same. The central object has a mass of approximately 297 million times the mass of our Sun, 4,297,000 solar masses. The entire Sun, with everything it contains, multiplied by 4 million, packed into a region of space so compact that S2 at its closest approach is still 4 times farther away from it than Neptune is from our Sun. Which means whatever this object is, it fits inside the orbit of Mercury around our Sun with room to spare. 4 million solar masses, inside Mercury's orbit, producing no detectable visible light. There is only one category of object in physics that can account for this. One phenomenon, predicted mathematically before anyone dared believe it could exist in nature, that allows mass of this magnitude to be concentrated in a region of space this small, while emitting almost nothing. We will come to it in full detail very shortly, but before we do, understand what the stars themselves told us. The stars did not merely suggest the presence of this object. They proved it, in the most demanding scientific sense of that word. The gravity collaboration, using an extraordinary optical interferometer at the Very Large Telescope in Chile, tracked S2 through its 2018 closest approach, with such precision that they were able to detect 2 distinct effects predicted by Einstein's general theory of relativity. First, the gravitational redshift, the stretching of S2's light to longer wavelength as it climbed out of the intense gravitational field at periapsis, exactly as general relativity predicts. Second, the Schwarzschild precession, the slow rotation of the ellipse of S2's orbit around the central point, an effect so subtle it requires decades of observation to accumulate, but measurable, confirmed, consistent with the predictions of general relativity to extraordinary precision. In other words, the center of our galaxy is not just a place where an unusual object happens to sit. It is a place where the fabric of spacetime is bent strongly enough that the oldest and most tested theory in physics, a theory built on the idea that mass curves space and space curves the path of light and matter, announces itself in the motion of a star. 2 scientists spent their careers making this possible. Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics led competing research groups for nearly 3 decades, each independently tracking the S-stars with increasing precision. Each arriving at the same conclusion from different instruments and different approaches, their results confirming and reinforcing each other's, building a case so overwhelming that in 2020, the Nobel Prize in Physics was awarded to both of them, along with the theoretical physicist Roger Penrose for exactly this work. The prize was awarded for the discovery of a supermassive compact object at the center of our galaxy. Compact object is the careful, formal language of physics. It means an object so dense that ordinary physics cannot explain it. An object whose existence points toward something more extreme than any ordinary matter can produce. But we need to call it what it is, what the stars were orbiting, what bent space around S2's path, what swallowed 4 million suns and gave back almost no light, what has sat at the center of the Milky Way for billions of years, invisible and immovable, the gravitational anchor of everything we have ever called home. It is a black hole. Not a stellar black hole, the kind born when a single massive star collapses at the end of its life. Something far older, far larger, far stranger than that. It is a supermassive black hole, and it has a name. In the next part of this journey, we are going to go directly to it. We are going to understand as precisely and as honestly as the science allows what it actually is, what it looks like when you get as close as light will let you, how it moves, how it feeds, how it sleeps, and what it has been doing for the last 200 years. Because as quiet as it appears tonight, the evidence suggests it is not entirely asleep. And the first image ever taken of it, released to the world in 2022, changed the way every human being on Earth was able to understand where we live. Before we go any further, we need to do something that most explanations of black holes skip over entirely. We need to discard the name. Not permanently. The name will come back. But for just a moment we need to set aside the phrase black hole, because those two familiar words carry so much cultural weight, so many science fiction images. So many dramatic visualizations of swirling vortices and glowing accretion disks, and ships being pulled helplessly toward a point of no return, that they actually make it harder to understand what this thing genuinely is. The name suggests emptiness. It suggests absence. A hole is a nothing, a gap, a missing piece. And what sits at the center of the Milky Way is not an absence. It is not a nothing. It is, in the most precise physical sense, the most extreme concentration of something that the universe is capable of producing. So let us start with what it actually is. When matter collapses under its own gravity into a small enough space, something extraordinary happens to the fabric of spacetime around it. Gravity, which Einstein described not as a force but as a curvature of space and time caused by mass, becomes so intense in the region immediately surrounding the collapsed object that the curvature stops being a gentle slope and becomes, in effect, a cliff, a point of no return, a boundary in space around which the mathematics of escape velocity reaches and then exceeds the speed of light itself. That boundary is called the event horizon. Beyond the event horizon, nothing that we know of in the universe can move fast enough to escape. Not a rocket, not a particle, not a photon of light, not information of any kind. The event horizon is not a physical surface. There is no wall, no membrane, nothing you could touch or see if you crossed it. It is a mathematical boundary, a threshold defined entirely by the relationship between mass, distance, and the speed of light. Cross it traveling inward, and you have left the observable universe permanently. Whatever happens on the other side stays on the other side, not because of secrecy but because of geometry. The geometry of spacetime beyond the event horizon points only inward, only toward the center, in every direction simultaneously. There is no out. There is only further in. The object inside the event horizon, the thing that caused the curvature, the collapsed mass at the mathematical center, is called the singularity. And here physics must be honest with us. We do not know what the singularity actually is. Our best theories break down before they get there. General relativity, which describes gravity, predicts the singularity but cannot describe its internal state. Quantum mechanics, which describes the behavior of matter at the smallest scales, does not have a language for the conditions at the center of a black hole. The singularity is, in the most rigorous sense, a place where our current understanding of nature reaches its limit and goes silent. This is not a failure of science. It is an honest accounting of what we know versus what we do not. Now, there are different kinds of black holes. Stellar black holes form when a massive star, many times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity in a catastrophic event. They typically have masses between a few and a few dozen solar masses. Then there are intermediate mass black holes, objects in the range of thousands to hundreds of thousands of solar masses, rarer and less well understood, occupying a middle ground. And then there is a third category, an entirely different class of object that appears to inhabit the centers of most large galaxies in the observable universe, objects so massive that even the word massive fails to carry their full weight. Supermassive black holes. These are not scaled-up versions of stellar black holes. They are something apart. Something that did not simply form when one star collapsed, but grew and accumulated and merged over billions of years of cosmic history, consuming gas, dust, entire star clusters, and in some cases other black holes, steadily accreting mass the way a stone rolling downhill gathers soil. Their masses range from millions to billions of solar masses. Their event horizons, correspondingly, are enormous on stellar scales, though microscopic on galactic ones, and they appear, without exception, in every galaxy large enough to have one at the center. The one at the center of the Milky Way is called Sagittarius A star, SGR-A, written with an asterisk that carries its own meaning, borrowed from the notation of excited atomic states in physics. Excited, energized, unusual. Even the symbol in its name suggests it is something in a heightened condition. Its mass is 297 million times the mass of our Sun, not approximately, not roughly. That number, refined over 30 years of orbital measurements to extraordinary precision, sits with a measurement uncertainty of plus or minus about 12,000 solar masses, which on the scale of 4 million is less than a fraction of a percent. We know this mass as well as we know many things in astronomy. We have weighed it, using the stars, but what does 297 million solar masses look like as a physical object? Think about our Sun for a moment. Our Sun contains more than 99.8% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, every particle of dust and gas in the entire solar system combined, all of it, makes up less than 0.2% of the solar system's mass. The Sun is not just large. It is the solar system in any meaningful gravitational sense. And now multiply that object, the entirety of our Sun, by 4,297,000. Pack all of that mass into a single region of space. The event horizon of SGR-A, the boundary of no return, has a diameter of approximately 24 million kilometers. That sounds vast, and in absolute terms it is, 24 million kilometers. But compare it to the scale of our solar system, and it shrinks dramatically. Mercury's orbit around the Sun has an average diameter of about 116 million kilometers. The event horizon of SGR-A, containing 4 million suns, sits entirely within an area roughly one-fifth the size of Mercury's orbit. If you placed SGR-A where our Sun is, Mercury would orbit it easily, comfortably, with enormous room to spare, unaffected by the event horizon, pulled by the gravity of 4 million suns, the way it is currently pulled by the gravity of one. This is, in the calmest possible terms, staggering. Now let us talk about what we can actually observe. Because SGR-A cannot be seen directly, cannot reveal itself through ordinary light, our knowledge of it rests on inference on the behavior of everything near it. On the radio waves and infrared emissions and X-ray flares produced by the hot turbulent material immediately surrounding the event horizon as it spirals inward. And until very recently, what we had were essentially data points, numbers, mathematical profiles, the shape of something enormous, described entirely in the language of its effects. Then, on May 12, 2022, that changed. The Event Horizon Telescope collaboration released the first direct image of Sagittarius A, a single historic photograph, assembled not from light collected through a single lens, but from data harvested simultaneously by 8 radio telescope arrays spread across the globe in Hawaii, in Chile, in Arizona, in Spain, in the South Pole, linked together into a virtual instrument with an effective diameter equal to the diameter of the Earth itself. What that image showed was this: a bright, uneven ring of glowing orange gold, slightly thicker on one side than the other, surrounding a dark central region. The ring is not the black hole. The ring is light. It is the glow of gas and plasma heated to millions of degrees as it swirls near the event horizon, emitting radiation as it compresses and collides and accelerates in the final spiral inward. The dark region at the center, the shadow, the absence of light at the heart of the ring, is the silhouette of the event horizon itself, the point at which the light bends too severely to reach us, the boundary that defines the edge of our knowledge. It took years to produce that image. Not years of waiting for clear skies or better technology, but years of computation, of processing petabytes of hard drives physically flown from observatories around the world to central computing facilities, of running thousands of different image reconstruction algorithms to find the ones consistent with the raw data. The challenge was not just distance. SGR-A is 27,000 light-years away, and its event horizon, small as it is in relative terms, subtends an angle in our sky roughly equivalent to the size of a donut sitting on the surface of the moon. And SGR-A did not make it easy. Unlike the black hole at the center of the galaxy M87, which sits quiet and steady enough that a single long-exposure image can capture it cleanly, SGR-A moves. The plasma surrounding it orbits the event horizon in just a few minutes. While the EHT was collecting data over hours-long observation windows, the region being photographed was changing multiple times per hour, like trying to photograph a spinning top by combining images taken days apart. The astronomers had to develop entirely new mathematical techniques to compensate for this motion, averaging across thousands of plausible images, finding the consensus among all of them, before they could produce something that faithfully represented the real structure. That is what it took to see it. And what does it spin like? SGR-A rotates, of course it does. Almost everything in the universe that is massive enough rotates, because the gas and matter that fell into it to build it up over billions of years almost certainly carried angular momentum, the property of rotating matter that must be conserved unless something deliberately removes it. The current best estimate of SGR-A*'s spin parameter is 0.90, on a dimensionless scale where 0 is perfectly non-rotating, and 10 is the theoretical maximum, beyond which the mathematics of general relativity break down entirely. A spin of 0.90 means SGR-A is rotating at 90% of the maximum rate physically possible for an object of its mass. It is spinning almost as fast as physics will allow. At the event horizon, that spinning does something remarkable. It drags spacetime itself around with the rotation, the way a spinning ball dragged through honey would pull the honey around with it. This effect is called frame dragging, or the Lenz-Thirring effect, and near a rapidly spinning black hole it becomes powerful enough to force the orbits of surrounding objects to precess, to tilt, to realign with the plane of rotation. The black hole is not just sitting there being massive. It is actively reshaping the geometry of the space immediately surrounding it. Now here is where the most recent science becomes genuinely extraordinary. In March 2024, the Event Horizon Telescope collaboration released new observations of SGR-A, this time in polarized light, a wavelength of observation that is sensitive to the structure and orientation of magnetic fields. What they found surprised even experienced researchers. SGR-A is surrounded by strong, organized, highly structured magnetic fields spiraling outward from the edge of the event horizon in a pattern, strikingly similar to the magnetic fields found around M87, the much larger black hole in the galaxy Messier 87, whose behavior we have been able to study in much greater detail. This similarity is important for a reason that will become clearer as we travel further outward from the center tonight. Those organized magnetic fields in M87 are believed to be responsible for launching an enormous jet of plasma from the black hole's poles, shooting material far out into surrounding space. If SGR-A has the same magnetic structure, and the new data strongly suggests that it does, then SGR-A may harbor a hidden jet. A jet that has not yet been detected, but which may be responsible for structures we will encounter later in this journey. And what about its behavior right now, in the present? SGR-A is categorized as an extremely low-luminosity active galactic nucleus. This is the careful, technical way of saying it is nearly completely dormant. By the standards of supermassive black holes, it eats almost nothing. The amount of material falling into SGR-A at any given moment is extraordinarily small, feeding at a rate billions of times lower than a typical quasar. This is why it produces almost no detectable light. It is, in the language of astronomy, in a quiescent state, sleeping. But sleeping is not the same as completely still. Observations made by NASA's James Webb Space Telescope throughout 2023 and 2024, studied by a team led by astrophysicist Farhad Yousefzadeh at Northwestern University, and published in 2025, revealed that SGR-A is, in the words of the research team, always bubbling with activity and never reaches a steady state. The JWST captured something the resolution of previous infrared instruments had missed entirely. A near-constant barrage of flickers, sparks, and sudden intense flares in the infrared emission from the region immediately surrounding the event horizon, changing over timescales of minutes, never the same twice, restless and unpredictable even in its dormant phase. Every time the team observed it during that period, something different was happening. No two observations were alike. It is not a still lake. It is a lake that appears still from a distance but seethes with constant small motion at its surface. And then there is the evidence of a more dramatic recent event. NASA's IXPE, the Imaging X-ray Polarimetry Explorer, has been mapping the X-ray light echoing through the molecular clouds surrounding the galactic center, and what it found has startled researchers. Approximately 200 years ago, SGR-A was not dormant. It woke up. It consumed a significant quantity of nearby gas and other material, and the burst of high-energy radiation from that feeding event traveling outward at the speed of light is still echoing through the surrounding gas clouds today, illuminating them in X-rays the way a flashbulb fired in a dark room continues to illuminate the walls after the flash itself has ended. The flash fired 200 years ago, as we measure it from Earth. The illumination has not yet fully faded. 200 years ago in human time corresponds to roughly the early 19th century. While Beethoven was composing symphonies and the first steam locomotives were being tested in England, the black hole at the center of the Milky Way was feeding. It woke up. It ate. And then it went back to sleep. And finally, consider this. A study published in September 2024 by researchers at the University of Nevada Las Vegas, using data from the Event Horizon Telescope and surrounding observations, found compelling evidence that SGR-A itself was not born as a single object. The analysis suggests that the supermassive black hole at the heart of the Milky Way is likely the product of an ancient merger of two black holes, each enormous in their own right, spiraling toward each other across millions of years, drawing closer under the relentless pull of mutual gravity, until they finally collided and merged into a single object of even greater mass. The center of our galaxy is itself the product of a collision, an ancient catastrophe preserved in the geometry of spacetime at the heart of everything. This is what sits at the center of the Milky Way, not a bright, warm cluster of stars, not a gentle, luminous core, a collapsed region of spacetime, 297 million times the mass of our Sun, spinning at 90% of the maximum rate physics allows, surrounded by strong, organized magnetic fields that may power a hidden jet constantly flickering, with the turbulence of infalling gas, awakening periodically to feed silent between meals, and built perhaps from the wreckage of a collision between two black holes that happened in the deep, formless past of our galaxy's history. It is ancient. It is almost completely dark. It is, by any reasonable measure, the most extreme object within tens of thousands of light-years of the planet you are sitting on right now. And it is not alone, because the black hole is only the beginning of what lives there. Around it, in the hundreds of light-years surrounding the event horizon, exists an environment unlike anything else in the known galaxy. An ecosystem, if you can use that word for something so violent. A neighborhood of young stars that should not exist, of molecular clouds drifting with organic chemistry, of extreme magnetic fields and cosmic rays and temperatures that swing between nearly absolute zero and millions of degrees within the same region of space. And in that neighborhood, astronomers have recently found something extraordinary. Objects that have survived right at the edge of the event horizon, in conditions that should have torn them apart long ago. Stars being born in places where birth should be impossible. And in December 2024, a signal so precise, so mathematically regular, that if it is confirmed, it will give us a cosmic clock ticking inside the most extreme gravitational environment our galaxy has to offer. Here is the question I want you to hold as we move into that neighborhood. If the black hole itself is surrounded by conditions this extreme, what does it mean that anything at all can survive there? What does it mean that life, or the chemistry that might eventually become life, exists in the molecular clouds within a few hundred light-years of this object? Drop your thoughts in the comments below. Because what comes next, the true portrait of the galactic center environment, is more surprising than almost anything we have covered so far. We have arrived at the heart. We have named it, weighed it, photographed it, watched it flicker and feed and sleep. We have traced the orbits of stars racing around its event horizon at 25% of the speed of light. We have measured the spiral of its magnetic fields and found the echoes of a feeding event that happened while humans were writing symphonies. And if everything we have covered so far were the whole story, it would already be one of the most extraordinary things in the history of scientific discovery. But SGR-A does not exist in isolation. No object in the universe does. Every massive body exists inside a neighborhood, surrounded by the material it has attracted and repelled and shaped over billions of years. And the neighborhood of SGR-A, the few hundred light-years immediately surrounding the galactic center, is not merely extreme in the way that deep space is extreme, cold and empty and vast. It is extreme in the opposite direction. Dense, hot, violent, turbulent, magnetically charged, flooded with radiation, and yet, against every expectation, teeming with activity, with chemistry, with stars, with things that should not exist there and yet, stubbornly, defiantly, do. This section of our journey requires us to zoom out from the event horizon by degrees. moving outward from the very innermost region through each successive layer of the galactic center environment, like peeling back the concentric rings of an onion each one, revealing a new set of conditions, each one stranger than the one before. The innermost layer, sitting just outside the event horizon, is a structure called the circumnuclear disk. It is a ring, or more precisely a torus, a thick donut shape of dense molecular gas and dust orbiting SGR-A at a distance of roughly 2 to 7 light-years from the event horizon. Compared to the scale of the galaxy, this is an absurdly small distance, 2 to 7 light-years. The nearest star to our Sun, Proxima Centauri, sits 4 light-years away. The circumnuclear disk orbits SGR-A at distances comparable to the space between us and our nearest stellar neighbor. At that range, the gravitational influence of 4 million solar masses is enormous. Gas and dust in the disk are being continuously shredded, heated, ionized, and in some regions slowly stripped away, drawn inward toward the event horizon on timescales of thousands to millions of years, serving as the primary fuel supply for whatever feeding events SGR-A occasionally indulges in. The inner edge of the circumnuclear disk, where it faces the black hole most directly, is being steadily eroded by the intense radiation produced by the hot gas and plasma immediately surrounding SGR-A. The outer edge grades gradually into the broader galactic center environment. It is not a clean boundary in either direction. It is a slow, complicated negotiation between gravity pulling inward and radiation and magnetic pressure pushing outward, with the disk itself caught in the middle, slowly losing material on one side while accumulating fresh gas on the other. Moving outward from the circumnuclear disk, we enter the domain of the S-stars, which we have already met. But there is something about this cluster that we did not fully discuss, something that becomes more remarkable the longer you sit with it. The S-stars are not old stars. They are not the ancient, red, slow-burning stars you might expect to find in a region of space so far from any current stellar nursery, so close to an object that should by rights be destroying everything in its vicinity. Many of the S-stars are young, hot, blue, and massive. They are stars that formed at most a few million years ago, not billions, millions. This is a problem, a serious, unresolved, deeply puzzling problem. Young, massive stars do not simply appear. They are born inside enormous molecular clouds, vast reservoirs of gas and dust that compress slowly under their own gravity over millions of years, eventually becoming dense enough for nuclear fusion to ignite at their cores. This is a gentle, fragile process, easily disrupted by external forces. Strong tidal forces, the kind produced by a supermassive black hole, should tear apart molecular clouds before they can compress enough to form stars, shredding them in the same way a moon moving too close to a planet gets pulled apart by differential gravity. The region immediately around SGR-A should be a star formation desert. The tidal forces there are simply too powerful for any molecular cloud to hold itself together long enough to birth a star, and yet the young stars are there. Astronomers call this the paradox of youth. It has no completely satisfying resolution. Several competing hypotheses exist. Perhaps the stars formed in a region farther from SGR-A and then migrated inward over millions of years, dragged by gravitational interactions with other stars and with the disk. Perhaps the molecular gas in the immediate galactic center is dense enough, or turbulent enough, or magnetically supported in ways unusual enough, that star formation can proceed under conditions that would sterilize a quieter environment. Perhaps, as some models suggest, a massive disk of gas fell into the galactic center a few million years ago and fragmented quickly, under its own instabilities, forming stars before the tidal forces had time to stop it. We do not know. This is a live question in galactic astronomy, actively debated, with new observations adding constraints and new models being proposed and tested. What we do know is that the stars are real, they are there, and their presence is telling us something about the galactic center environment that our current models do not yet fully capture. Moving outward a little further, we encounter what might be the strangest individual objects in the entire galactic center environment, the G-objects. These are a handful of compact, dust-shrouded sources that follow elongated orbits around SGRA, similar in shape to the S-star orbits, but surrounded by thick envelopes of gas and dust that make them appear, at first glance, like dense clouds of material rather than stars. The most famous of them is called G2, detected in the late 2000s on an approach trajectory toward SGRA that predicted it would make a very close pass within a few hundred astronomical units of the event horizon around 2014. The astronomical community watched this event with enormous anticipation. Predictions varied. Some researchers expected G2 to be stretched and partially disrupted, a process called spaghettification, as SGR**'''''''S tidal forces pulled harder on the side of G2 nearest the event horizon than on the far side. Some expected a significant brightening of SGRA, a feeding event, as disrupted material from G2 spiraled inward. A number of papers predicted that 2014 would produce the brightest observed activity from SGRA in decades. None of that happened. G2 passed its closest approach, rounded SGRA and continued on its orbit intact. Stretched and tidally distorted, yes, but not destroyed, not consumed. It survived. The most natural explanation for this survival, and the one now most widely accepted, is that G2 is not a pure cloud of gas and dust. There is a star inside it. A young star, still embedded in the dense envelope of material from which it formed, using that envelope as a kind of armor against the tidal forces trying to tear it apart. G2, under this interpretation, is not a cloud that happened to wander near a black hole. It is a young star in an unusually early stage of its development, navigating the extreme inner environment of the galactic center while still wrapped in its birth cocoon. Then, in 2024, an even more remarkable discovery was made in this inner region. A research team led by astrophysicist Florian Pasker identified a binary star system orbiting close to SGRA, designated D9. A binary star system is two stars gravitationally bound to each other, orbiting their common center of mass, the way two dancers might circle each other while also both circling the stage. What makes D9 extraordinary is its location. It is the first known binary star system found in close orbit around a supermassive black hole. The tidal forces at that range should, by many theoretical estimates, have disrupted the pair long ago. The gravitational gradient across the separation between the two stars should be strong enough to gradually pull them apart, like two rafts being pulled in slightly different directions by a river current. And yet, observations made with the ARIS instrument at the Very Large Telescope show that D9 remains intact, its orbit stable, both stars continuing to circle each other while together circling SGRA. These results confirm something that had not been fully appreciated before. The galactic center is not only destructive, it can be, in ways we are only beginning to understand, surprisingly stable. The environment that should annihilate complex structures is, for certain configurations, for certain combinations of mass and orbital geometry and shielding, compatible with their survival. And then, in December 2024, researchers at Columbia University working with the Breakthrough Listen program reported the detection of a tantalizing signal from near SGRA. A rapidly repeating pulse, occurring every 19 milliseconds, detected in radio wave observations of the galactic center. If this signal is confirmed as what it appears to be, it would represent the detection of a millisecond pulsar, a rapidly spinning neutron star, within the immediate vicinity of SGR-A. This matters enormously, for reasons beyond the remarkable fact of its existence in such an extreme environment. Pulsars are nature's most precise clocks. They spin with a regularity that rivals atomic clocks built in physics laboratories, their pulses arriving at intervals so consistent that even the smallest perturbations of their orbits can be detected as tiny deviations in timing. A pulsar in close orbit around SGR-A would allow physicists to probe the curvature of spacetime near a supermassive black hole, with precision far beyond what stellar orbits alone can provide. It would become, in effect, a natural instrument for testing general relativity in the strongest gravitational field accessible to human observation. The signal remains unconfirmed as of our most current knowledge. But the implications, if confirmed, are profound enough that the Galactic Center Pulsar Search has become one of the most active observational programs in radio astronomy. Now let us zoom outward once more, to the broader neighborhood of the galactic center, the region known as the Central Molecular Zone. The Central Molecular Zone, or CMZ, is the roughly 900 light-year wide region centered on SGR-A, defined by an enormous concentration of molecular gas, unlike anything found elsewhere in the galaxy. This region contains somewhere between 50 and 60 million solar masses of molecular hydrogen, representing somewhere between 5 and 10% of the entire Milky Way's molecular gas supply, crammed into a volume that represents less than 1/10 of 1% of the galaxy's total volume. It is the most gas-rich region of the Milky Way by an enormous margin. Dense molecular clouds, some large enough to qualify as among the most massive such objects in the galaxy, cluster here in concentrations that dwarf the cold gas reservoirs found in the outer arms. The largest and most studied of these clouds is Sagittarius B2, sitting roughly 390 light-years from SGR-A, and it is, among astronomers who work on interstellar chemistry, one of the most famous objects in the sky. SGR-B2 is a cloud of staggering proportions, roughly 3 million solar masses of gas and dust packed into a region perhaps 150 light-years across. It is one of the most active star-forming regions in the entire galaxy, containing dozens of newly formed massive stars and hundreds of embedded stellar nursery still in the process of collapsing. But what makes SGR-B2 particularly extraordinary, what has made it the subject of intense spectroscopic study for decades, is its chemistry. Interstellar molecular clouds are chemical laboratories. The gas within them, frozen to temperatures just barely above absolute zero in the densest cores, shielded from external radiation by the sheer thickness of the surrounding dust, hosts a rich collection of molecular species. In ordinary clouds in the outer galaxy, the chemistry is relatively simple: water, carbon monoxide, ammonia, methane, the familiar small molecules of cold chemistry. Sagittarius B2 contains something more complex. Glycolaldehyde, a simple sugar, has been detected there in the gas phase. Ethanol, vinyl alcohol, acetic acid, aminoacetonitrile, a molecule considered a potential precursor to glycine, the simplest amino acid, and a fundamental building block of proteins. These are not exotic laboratory compounds. They are molecules that appear in discussions of the chemistry of life. They are drifting, cold and dispersed, through an enormous gas cloud a few hundred light-years from the galactic center, near one of the most violent objects in the Milky Way. Life, or the chemistry that might eventually produce it somewhere under the right conditions, does not organize itself exclusively in quiet, safe, gentle corners of the galaxy. It emerges from the same processes, the same atoms, the same physical and chemical reactions that also produce black holes and supernovae and extreme magnetic fields. The molecular clouds near the galactic center are not outside the story of life. They are part of it. The CMZ as a whole is not simply dense with gas. It is dense with everything. Cosmic rays, high-energy particles produced by supernovae and other violent events, flood this region at intensities roughly 1,000 times higher than those found in the outer galaxy where our sun resides. The magnetic fields here are not the gentle, diffuse fields of the galactic disk. They are structured, strong, twisted, running perpendicular to the galactic plane in ways still not fully understood, their intensity roughly 1,000 times greater than the average field at our position in the galaxy. The gas temperature varies wildly across the region, with some molecular clouds maintaining cores barely above absolute zero, while adjacent material reaches millions of degrees, heated by the radiation pouring from nearby young stars and from the ambient high-energy environment of the galactic center. Here is the callback to where we began tonight. Remember the familiar illustration. The warm, orderly, gently glowing core of the spiral galaxy, nestled comfortably at the center like a fireplace in a living room. What we have been describing for the past several minutes is what actually lives there. A 4 million solar mass black hole spinning at 90% of maximum, surrounded by a disk of gas, feeding slowly inward, surrounded by young stars, that should not exist, surrounded by strange dust-shrouded objects defying the tidal forces that should shred them. Surrounded by a molecular cloud 3 million times the mass of the sun, drifting with the chemical ingredients of life, all of it embedded in a region of space, 1,000 times denser, 1,000 times hotter in places, 1,000 times more magnetically charged than the galactic neighborhood we live in 26 light-years away. The comfortable picture is gone. What replaced it is stranger, more violent, and in a way more beautiful. And yet all of this, the black hole, the S-stars, the binary system that should be shredded, the pulsar ticking in the dark, the molecular chemistry drifting in the cold, all of it together, constitutes only the innermost room of a much larger structure. A structure so vast, so unexpected, so energetic that when astronomers first identified it, there was a genuine moment of collective disbelief. A structure that tells us SGR-A was not always the dormant, barely feeding giant we observe today. A structure that is, in the most literal sense, the scar left by a version of the galactic center we have never witnessed. A version so dramatically different from what we see now that it challenges our entire understanding of what kind of galaxy we live in. We need to zoom out much further, not hundreds of light years, not thousands. We need to zoom out to the full scale of the Milky Way itself, and then beyond it, above it and below it, into the space where no one expected to find anything at all. Because sitting directly above and below the galactic center, completely invisible to ordinary light, extending far, far beyond the disk of stars and gas we call our galaxy, are two enormous structures, two ghostly lobes of energy, each one tall enough to dwarf the entire Milky Way's disk. Each one shaped by an event so energetic it boggles the imagination. Each one a silent, enormous testament to a time when what sleeps at our galaxy's center was wide, violently, catastrophically awake. Here is the question I want you to carry with you into what comes next. If the galactic center, even in its current dormant state, is this extreme, what do you think it looked like when it was truly active? What would it have felt like to live in a galaxy with an awakened center? Tell me in the comments. Because the answer to that, when we look at the evidence, is more dramatic than you might expect. We need to pull back now. Not by hundreds of light years, not by thousands, but by tens of thousands. We need to step back far enough that the galactic center, with everything we have just explored, the black hole and the S-stars, and the circumnuclear disk, and the molecular chemistry drifting cold in Sagittarius B2. All of it shrinks to a single bright point at the center of a much larger picture. We need to see the Milky Way as a whole. Not from inside it, not as the faint river of light we see on dark nights, but as a structure, a complete object, viewed from a distance sufficient to take it all in. Imagine it for a moment. The full galaxy spread out before you. A flat, luminous disk, roughly 100,000 light-years in diameter. From above, the spiral arms curve outward in great sweeping arcs, lit by the blue-white fire of young, massive stars forming in the dense gas lanes. From the side, the disk is remarkably thin for its width, perhaps 1,000 light-years thick at the position of our Sun, thickening toward the center where the galactic bulge swells slightly above and below the midplane. Surrounding the disk, an enormous, nearly empty spherical halo, sparsely populated by ancient globular clusters and individual old stars, relics of the galaxy's earliest history. And at the center, the bright condensed core of the bulge, which we now know hides a 4 million solar mass black hole in a state of almost complete dormancy. From the outside, the Milky Way would look at first glance like a quiet spiral, orderly, structured. A galaxy in a settled, mature phase of its life, its most violent star formation activity long past, its central engine essentially switched off. That is what it would look like. Invisible light, change the wavelength. Switch from optical light to gamma rays, high-energy photons produced by the most energetic processes in the universe, collisions between cosmic ray electrons and photons, the annihilation of matter and antimatter, the violent shock fronts of outflowing plasma. Switch to gamma rays and look at the same galaxy. And you will see something that should not be there, something enormous. Something completely invisible in ordinary light but blazing, almost overwhelming in the gamma-ray sky. Two vast lobes of emission, one rising directly above the galactic center, one plunging directly below it, each one roughly spherical, each one extending approximately 25,000 light-years from the galactic plane. Together, top to bottom, they span 50,000 light-years. The disk of the Milky Way, the structure that contains all 100 to 400 billion stars, is roughly 100,000 light-years across and perhaps 1,000 light-years thick at our position. These structures rise above and below that disk for 25,000 light-years each. They are half as tall as the galaxy is wide. They are 25 times taller than the disk is thick. They dwarf, in terms of vertical extent, almost everything that most people mean when they say the words the Milky Way. These are the Fermi bubbles. They were discovered in 2010 by a team led by astrophysicist Meng Su at Harvard, using data from NASA's Fermi Gamma-ray Space Telescope. Launched in 2008 to map the gamma-ray sky with unprecedented sensitivity and resolution. Fermi had been accumulating data for 2 years when the analysis revealed the bubbles clearly rising unmistakably above and below the galactic plane, centered precisely on the galactic center structured, and bounded in ways that immediately suggested they were not a diffuse background glow, but a specific, coherent pair of objects. The discovery, when published, caused a genuine stir in the astrophysics community. Nothing of this scale centered on the Milky Way's core had been expected or predicted. Nothing in the existing models of our galaxy's current activity had prepared astronomers for lobes of gamma-ray emission this large, this bright, this symmetrically placed. What makes the Fermi bubbles genuinely startling, beyond their sheer size, is their edges. They are sharp, extraordinarily, almost unnervingly sharp. The boundary between the interior of each bubble and the surrounding halo is not a gradual fade, not the kind of soft, indistinct edge you would expect from a diffuse emission region slowly dissipating into the surrounding medium. It is a crisp, well-defined line, a boundary. The kind of edge that tells you this structure is not the passive remnant of some slow, diffuse process, but something that was actively inflated like a balloon pushed outward from within, by a sustained internal pressure against an external medium. maintaining its coherence and its shape over an enormous span of time. Inside that sharp edge, the gamma-ray emission is remarkably uniform in spectrum across the entire interior of each bubble. Not brighter at the center, not fainter at the edges. Uniform. This spectral uniformity is itself a major clue to origin, because it constrains the age and mechanism of the emission in ways that a non-uniform distribution would not. It tells us that whatever created these bubbles deposited its energy relatively quickly, not in a slow, steady trickle, but in an event, or a series of closely spaced events, that inflated both lobes to their current size before the emission had time to develop significant internal gradients. Then in 2020, the picture expanded dramatically. The German-Russian EROSITA X-ray telescope, part of the Spectre-RG satellite, released an all-sky X-ray map of unprecedented sensitivity. And on that map, surrounding the Fermi bubbles, astronomers found something even larger. Two enormous lobes of soft X-ray emission, also centered on the galactic center, also roughly symmetric above and below the galactic plane, each one extending approximately 45,000 to 50,000 light-years from the galactic disk. The EROSITA bubbles, larger than the Fermi bubbles, older, more diffuse at their edges, representing, most likely, an earlier phase of the same outflow or a separate energetic event whose signature has had more time to spread and cool. Combined, the EROSITA bubbles span roughly 100,000 light-years from top to bottom. They are as tall as the galaxy is wide. If you could see them with your eyes, if they emitted in the visible spectrum, they would dominate the view of our galaxy from outside. The spiral disk would be a thin, bright wafer sandwiched between two enormous glowing spheres, like a coin balanced between two balloons. We live inside this system. These structures are above and below us right now, invisible to our eyes, silent in our radio receivers, but real, vast, and still faintly glowing in wavelengths we need special instruments to detect. The galaxy we think we live in, the flat, quiet spiral, is in fact the calm middle of something far more dynamic, something that breathed out. Now we need to ask the question that matters most. What made them? Two major hypotheses have dominated the scientific literature since the Fermi bubbles were discovered, and neither one has been definitively confirmed. They are not mutually exclusive. They may both be partially correct. The first hypothesis is that the bubbles were inflated by jets launched from SGR-A itself during a past period of dramatically elevated activity. This is the active galactic nucleus scenario. Under this model, the supermassive black hole at the galactic center underwent a phase millions of years ago, during which it was consuming material at a rate enormously greater than today, feeding at a level that powered the launch of two relativistic jets, columns of energetic plasma shooting outward along the rotation axis of the black hole perpendicular to the galactic disk, drilling through the surrounding gas, heating and compressing it, and ultimately inflating the enormous cavities we see today as the Fermi and EROSITA bubbles. The energy required to inflate these structures is approximately 10 to the power of 55 ergs. This number is difficult to intuit at human scales. Consider it this way. A single supernova, the explosive death of a massive star, one of the most energetic single events in the universe, releases approximately 10 to the power of 44 ergs of energy. To inflate the Fermi bubbles through supernova energy alone would require something in the range of 100 billion individual supernova explosions. The bubbles contain, locked in their structure, the energy equivalent of 100 billion stellar deaths. Alternatively, that energy could have come from a single sustained accretion event at SGR-A, a phase of intense feeding lasting perhaps 1,000,000 years or more, during which the black hole was consuming material at rates comparable to those seen in low-luminosity, active galactic nuclei in other galaxies. Under this scenario, a study published in 2023 proposed that the jets responsible were likely misaligned slightly from the current rotation axis of SGRA, a detail that helps explain some of the subtle asymmetries observed in the bubble structure. The second hypothesis focuses not on SGRA itself, but on the concentrated burst of star formation that occurred in the galactic center region a few million years ago. Massive stars live fast and die violently. Each one terminates in a supernova and a nuclear starburst. A period of intense star formation in the galactic center could produce enough supernovae in close enough succession to drive a powerful galactic wind outward, along the path of least resistance which in a disk galaxy is perpendicular to the disk itself. Up and down rather than outward through the dense material of the disk. This wind, sustained over millions of years by the collective output of thousands of massive stars, could plausibly have inflated structures of the scale we observe. The scientific consensus, to the extent one exists, leans toward a combination of both processes, with some researchers preferring AGN jets as the primary driver and others favoring nuclear starburst winds. What is not in dispute is the timing. The event, or events, that inflated the Fermi bubbles occurred roughly 2 to 4 million years ago, based on the dynamics and cooling times of the emitting plasma. 2 to 4 million years ago. In terms of deep time, in terms of the 13.8 billion year history of the universe, this is the day before yesterday, the cosmological equivalent of last week. 2 to 4 million years ago, our ancestors, early members of the genus Homo, were walking the savannas of Africa. They were making stone tools. They may have been developing the early precursors of language. They were, by any measure, the most cognitively sophisticated creatures on Earth at the time. And above their heads, invisible to them, filling half the sky in gamma rays they had no way to detect, the aftermath of an event that reshaped the entire galactic center was glowing. The Fermi bubbles were already there, already expanding, already cooling from the violence of their creation when our most direct ancestors walked the Earth. Let us push further. Because if the Fermi bubbles were inflated by SGRA in an active phase, then we need to ask what SGRA looked like during that period. What the galactic center was doing while it produced enough energy to push structures 25,000 light-years above and below the disk. The answer is something called a Seyfert flare. A Seyfert galaxy is a type of galaxy with an unusually bright, energetically active nucleus, typically powered by a supermassive black hole accreting material at a rate far above what we observe in SGRA today. Some astronomers have proposed, based on the energy budget of the Fermi bubbles and the dynamics of the outflow, that the Milky Way underwent a Seyfert phase roughly 3 million years ago, during which SGRA was accreting material at a rate perhaps 1,000,000 times greater than its current rate, and was correspondingly 1,000,000 times more luminous. Think about what that would mean for the appearance of our galaxy from outside. Right now, the Milky Way is a normal, unremarkable spiral galaxy. From the Andromeda Galaxy, 2.5 million light-years away, it would appear as a faint smear of starlight, nothing unusual, nothing that would draw special attention. During a Seyfert phase, the center of the Milky Way would blaze. The galactic nucleus, currently one of the dimmest central engines in any nearby galaxy, would outshine it from billions of light-years away. A column of energetic plasma would shoot outward above and below the disk, glowing in X-rays and gamma rays, visible across intergalactic distances. The Milky Way would have looked from outside like an active galaxy, a quasar in miniature, a galactic lighthouse. And what would it have meant for life inside that galaxy at the time? Here we must be careful and honest. The effects of an active galactic nucleus on life elsewhere in the galaxy are real but complex, and depend enormously on geometry and distance. The most intense radiation would be confined largely to the jets themselves, narrow columns along the rotation axis, and to the innermost few thousand light-years of the galactic center. At the distance of the Sun, 26,000 light-years from the center, the increased radiation from a Seyfert phase would have been detectable but probably not biologically catastrophic. A significant increase in ionizing radiation reaching Earth's upper atmosphere, a measurable enhancement of cosmic ray flux, potentially some impact on climate through effects on the ozone layer. Not pleasant, not without consequences, but probably survivable for life already sheltered beneath several kilometers of ocean or rock. Some researchers have noted, though this remains speculative and is not scientifically mainstream, that the timing of certain mass extinction events in Earth's history, events around 2 to 3 million years ago, that coincided with significant ecological disruption and species turnover, may not be entirely unrelated to the activity level of the galactic center at that time. This is not an established causal link. It is an observation of possible coincidence, flagged by a small number of researchers, not yet supported by sufficient evidence to call it anything more than a hypothesis. But it is a reminder that the galactic center is not separate from us. We live inside its sphere of influence. Its history is, in some faint and attenuated way, our history too. Now Sgr A** sleeps. It is, in the language of observational astronomy, one of the most dormant supermassive black holes in the local universe. Its accretion rate is so low that it has been described as eating at a rate billions of times below its theoretical maximum. The Eddington limit, the theoretical maximum luminosity a black hole of given mass can sustain through accretion, represents a level of activity that Sgr A is currently reaching at a fraction of a percent of a percent. The sleeping giant is barely breathing, and yet we know it wakes up. We discussed the IXPE evidence already. 200 years ago, something fed. The X-ray echoes are still propagating through the surrounding molecular clouds, illuminating them from the inside like lanterns catching the light of a torch already past. That feeding event was modest by cosmic standards. A snack, not a meal. Sgr A stirred, consumed a little, and returned to sleep. But consider the question these facts collectively raise. If Sgr A was producing Seyfert-level luminosity a few million years ago, driven by accretion at rates millions of times its current level, and if it woke briefly just 200 years ago to consume nearby material, then its current dormancy is not a permanent condition. It is a phase. A long, quiet phase in the life of an object that has been energetically active before and will be energetically active again. The galaxy has a heartbeat. It is just very, very slow. There is material waiting to fall in. The circumnuclear disk feeds slowly inward. The central molecular zone, with its tens of millions of solar masses of cold gas, surrounds the central region like a vast reservoir. Stars die near the galactic center, their gas dispersed into the surrounding medium. And the long-range gravitational dynamics of the galaxy itself, including the approaching merger with the Andromeda Galaxy expected in roughly 4 billion years, will eventually disrupt gas reservoirs across the Milky Way, driving fresh material inward toward the center. Sgr A is not finished. Nothing this massive is ever finished. It is resting, and the Fermi bubbles still glowing softly above and below the galactic plane in gamma rays and X-rays, are the exhaled breath of the last time it truly woke up, still hanging in the air, still slowly expanding outward into the intergalactic medium. A monument to a moment of violence that our oldest ancestors may have walked beneath without the faintest knowledge of what blazed above them. Remember the image we started with tonight. The comfortable, tidy spiral, glowing warmly at its center, everything in its place, everything orderly and familiar. We have now seen what the center actually is. We have now seen the scars of its past activity, extending far above and below the disk, invisible to ordinary light but blazing in the frequencies of extreme physics. We have now seen that the galaxy we live inside is not the quiet, settled structure the textbook diagram suggested. It is a galaxy in a quiet phase between active ones. A galaxy whose central engine has been violent, is dormant, will be violent again. A galaxy still wearing the marks of its last great outburst like old burns on a healed skin. And we have one final zoom remaining, one last expansion of scale. One last shift of perspective, the most disorienting of all, that will reach back and retroactively change the meaning of everything we have discussed tonight, including the original question that started this journey. Because we have been asking, all this time, what sits at the center of the Milky Way? We have found it. We have described it with extraordinary precision and depth. And yet the very concept we have been using as our frame, the concept of a center, of a fixed, definable, singular point that everything else surrounds, is itself about to come apart. Not because the science was wrong, but because the universe is under no obligation to organize itself around the questions we bring to it. Before we go there, I want to ask you something more personal. If the Milky Way's central black hole fully reactivated, and our galaxy became a visible quasar from across the universe, what do you imagine that would mean for life on Earth, and for any other life that might exist in the galaxy? Drop your thoughts below. Because the answer and what comes after it reaches all the way back to the question of what we are, where we are, and what kind of universe we actually live in. We have traveled a long way tonight. We began with a flat spiral diagram on a classroom wall. We watched it crack when infrared light penetrated the dust and revealed stars moving at impossible speeds around a single dark point. We named that point, weighed it, photographed it, traced the magnetic field spiraling at its edge and the X-ray echoes of its most recent feeding. We explored the extraordinary neighborhood surrounding it, the young stars that should not exist, the binary system defying destruction, the molecular clouds drifting with the chemistry that may eventually become life somewhere, under the right conditions, in the right time. We pulled back far enough to see the Fermi bubbles, the exhaled breath of the last time the sleeping giant woke fully, still expanding outward above and below the galactic plane in the invisible frequencies of extreme physics. And now, we need to pull back one final time. Farther than we have gone yet. Farther, in fact, than any of the previous zooms prepared you for, because this last expansion of scale is not just about distance. It is about the framework we have been using all along, the word at the center of our original question. The assumption buried so deeply inside the way we framed tonight's journey that most of us never noticed it was an assumption at all. The word center. But before we arrive at the dissolution of that concept, we need to zoom out through the geography that surrounds us, because the journey matters as much as the destination, and each step outward adds something essential to what we are building toward. Step back from the Milky Way. Past the Fermi bubbles, past the EROSITA bubbles still cooling from their ancient inflation, past the sparse outer halo, where old globular clusters orbit in long, slow arcs like memories of the galaxy's earliest assembly. Pull back far enough that the Milky Way itself shrinks to a disk of faint light, 100,000 light-years across, which at this distance looks remarkably small. Pull back far enough to see our neighbors. We live in what astronomers call the local group. A gravitationally bound collection of galaxies, roughly 54 in total by current count, spread across a volume of space approximately 10 million light-years in diameter. Most of them are small. Dwarf galaxies, irregular galaxies, modest collections of stars gravitationally subordinate to the two dominant members of the group, which face each other across an intergalactic gulf of approximately 25 million light-years. One of those dominant members is us. The Milky Way, with its hundreds of billions of stars and its sleeping central engine, and its two enormous gamma ray lobes still glowing softly above and below its disk. The other is Andromeda. The Andromeda Galaxy, also called Messier 31, is the largest galaxy in the local group, somewhat larger than the Milky Way, containing perhaps 1 trillion stars to our estimated 200 to 400 billion. It is the most distant object visible to the naked human eye, a faint smear of light in the constellation Andromeda on dark, clear autumn nights, so far away that the photons reaching your retina when you look at it left their source too. 5 million years ago, before our genus Homo had yet appeared on Earth, Andromeda is approaching us, not slowly, not gently. It is moving toward the Milky Way at approximately 110 kilometers per second, and the models of its trajectory, refined by precise measurements from the Hubble Space Telescope and more recently from the Gaia satellite, indicate that in roughly 4 billion years, the two galaxies will begin a collision. Not a collision in the ordinary sense, not two solid objects striking each other, because galaxies are mostly empty space, and the stars within them are so widely separated that direct stellar collisions during a galaxy merger are extraordinarily rare. But the gravitational interaction between two structures, each containing hundreds of billions of stars, will be catastrophic on galactic scales. The spiral arms will be torn apart. Stars will be flung into new orbits. The two galactic disks will pass through each other, separate, return, pass through again, and over the course of perhaps 2 billion years of gravitational negotiation, merge into a single, larger, probably elliptical galaxy. Astronomers have already given this merged future galaxy a name, Milkomeda, or sometimes Milkdromeda. And at the center of Andromeda, right now, there is a supermassive black hole. It is designated M31 asterisk, and its mass is estimated at somewhere between 100 million and 200 million solar masses, between 25 and 50 times the mass of SGR-A. When Andromeda and the Milky Way eventually merge, these two black holes, separated today by 5 million light-years, will find themselves in the same galaxy. They will migrate toward the new merged center through the process of dynamical friction, the gravitational drag that massive objects experience as they move through a medium of surrounding stars and gas, each interaction bleeding a tiny amount of momentum from the black hole's relative orbit. Over millions of years, they will spiral closer and closer together. Eventually, if they get close enough, and models suggest they will lose the remainder of their orbital energy to gravitational waves, ripples in the fabric of spacetime propagating outward at the speed of light, and they will merge. Two supermassive black holes becoming one. A single object more massive than either. Another center eating another center. We will not be here to see it. The sun will have exhausted its hydrogen fuel in roughly 5 billion years, and Earth's surface will have been rendered uninhabitable long before the full merger completes. But the physics is real, the trajectory is set, and the outcome is not in doubt. Hold that image for a moment. Two black holes, each the gravitational anchor of an entire galaxy, spiraling together across millions of years, their final merger sending gravitational waves through spacetime itself, detectable in principle, across an enormous fraction of the observable universe. The centers of galaxies are not static, permanent fixtures. They are dynamic, evolving, merging objects, defined not by their location in some absolute cosmic geometry, but by the local gravitational dynamics that happen to concentrate mass at particular points during particular epochs of cosmic history. Now let us zoom out further still. Beyond the local group, in every direction, the universe is filled with galaxies. The Virgo cluster, containing over 1,300 galaxies, lies roughly 54 million light-years away. The Laniakea supercluster, the enormous superstructure of which our local group is a tiny peripheral member, spans approximately 520 million light-years, and contains an estimated 100,000 galaxies. And beyond Laniakea, in every direction, more superclusters, more filaments, more voids, the cosmic web of large-scale structure stretching in all directions as far as our instruments can see. The observable universe contains, by the most careful current estimates, somewhere in the vicinity of 2 trillion galaxies. 2 trillion. And the great majority of large galaxies, the spirals and ellipticals massive enough to have organized themselves around a gravitational center, harbor a supermassive black hole at that center. Some of those black holes are sleeping, as ours largely is. Some are feeding actively, their accretion disks blazing with radiation across enormous distances. The most energetic of the actively feeding ones are called quasars, objects so luminous that a single quasar can outshine an entire galaxy of 100 billion stars. All of that light produced not by the stars in the galaxy, but by a single supermassive black hole eating it close to its maximum rate. The black hole at the center of the galaxy Messier 87, which you may know as the first black hole ever directly imaged in 2019, is one of the most massive objects in the local universe. Its mass is approximately 65 billion solar masses, not millions, billions. It is roughly 1,500 times more massive than SGRA. Its event horizon is so large that our entire solar system, out to the orbit of Neptune, could fit inside it with room to spare. Its jet, the column of plasma launched along its rotation axis and powered by its magnetic fields, extends thousands of light-years into the surrounding space, visible in radio waves as a thin, bright needle stabbing outward from the galaxy's core. And SGRA, sitting quietly at the center of our galaxy, is what M87 asterisk would look like if it stopped eating. Or perhaps more accurately, M87 is what SGRA might have looked like billions of years ago if it had access to more material. They are the same category of object, differing by mass and by feeding rate. Calm and storm. The same physics, the same mechanism, the same category of extreme, just in different phases of the same long process. 2 trillion galaxies, most with a center. Most with a black hole at that center. The supermassive black hole is not an anomaly. It is not a local peculiarity of our particular spiral galaxy. It appears to be a universal feature of the large-scale structure of the universe, emerging wherever enough mass concentrates, wherever gravity has had enough time to accumulate and collapse and build something heavy enough to hold a galaxy together. Centers, then, are everywhere. Which means that in a very real sense, center means something different from what the word implies. Here is the deepest fact in all of cosmology, and the one that most quietly undermines everything we intuitively feel about the universe. The universe, as best as we can determine, has no center, not in the geometric sense, not a point from which all other points are equally distant in all directions, not a location you could visit. Not a place where things began, or where gravity is strongest, or where time is oldest. The Big Bang did not happen at a point. It happened everywhere simultaneously, as all of space itself expanded from an earlier, denser, hotter state. There is no location in the universe that corresponds to the site of the Big Bang, because the Big Bang was not an explosion in space. It was an expansion of space itself. Every point in the universe was there. Every point in the universe was the origin. Which means something extraordinary about where you are right now. You are at the center of your observable universe, not metaphorically, literally. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is centered precisely on the point where you are standing, sitting, lying down, reading these words, or drifting towards sleep. Another observer, located 10 billion light-years from you in any direction, would see themselves at the center of their observable universe. Their sphere and yours would overlap, but they would each be the center of their own. The universe is simultaneously centerless and composed entirely of centers, every observer their own, every point of observation the middle of everything that observer can see. And this is where the original question of tonight's journey begins to dissolve. What sits at the center of the Milky Way? We have answered it, beautifully, precisely, in extraordinary detail. A 4 million solar mass spinning black hole surrounded by one of the most extreme environments in the known galaxy, still wearing the exhaled ghost structures of its last great period of activity. Ticking quietly in the dark while the stars it was never supposed to birth continue to orbit it in defiance of the models. But the word center in the question carries an assumption. The assumption that the center of the Milky Way is a privileged location, a special place. The heart of something, the way a heart is the center of a body, the essential organ without which nothing else works. And while SGR-A is indeed the gravitational anchor of the Milky Way, the object whose mass defines the orbital structure of the galaxy's stars in the innermost regions, it is not the center of anything larger. It does not sit at the heart of the local group. It does not mark the middle of the observable universe. It does not even represent, within the Milky Way itself, a geometrically privileged point in the cosmic web of large-scale structure. It is a center the way any sufficiently massive object is a center, defined entirely by gravity. Defined by the local history of accumulation and collapse that happened to deposit 4 million solar masses in that particular point in space, roughly in the direction of the constellation Sagittarius. Had the initial conditions of the Milky Way's formation been slightly different, had the gas that became our galaxy collapsed from a slightly different configuration, the center might be elsewhere. It would still be a center. It would still be a black hole. It would just be somewhere different in the sky. Center is not a cosmic fact. It is a gravitational consequence, and we have been orbiting this consequence for 4-5 billion years. Our sun formed from a molecular cloud roughly 4-6 billion years ago, and almost immediately began its long orbit around the galactic center. In the time since, it has completed approximately 20 full orbits. 20 trips around a point containing 4 million solar masses, each trip taking between 225 and 250 million years. Each orbit a vast ellipse that we have never deviated from, that we will not deviate from, that continues today at the same stately pace it has always maintained. We are, in the most literal sense, in a committed relationship with SGR-A. It has never threatened us. At 26,000 light-years, its gravity is no more dangerous to us than the gravity of any other distant massive object. It does not pull us toward it in any way we notice. It simply holds the galaxy together, and in holding the galaxy together, holds everything in the galaxy in the long embrace of its rotation. There is no up from SGR-A. There is no down. There is only orbit, and the slow, patient geometry of mass and space and time, arranged not according to any human concept of center and edge, but according to the one rule the universe enforces consistently in every direction and at every scale. Gravity is patient. Gravity is thorough. And gravity, given enough time and enough mass, always builds something. What it built at the center of the Milky Way has been there since the galaxy itself was young, accumulated before the sun existed, before the Earth existed, before the molecular cloud that would eventually condense into our solar system had even begun to gather itself from the diffuse gas of the early universe. It will be there long after the sun burns out, long after the Milky Way merges with Andromeda. Long after any civilization on any planet in this galaxy could exist to ask questions about it. Black holes of this mass do not evaporate on any timescale relevant to human thought. They persist. They endure. They sit at the centers of things not because the universe designated them special, but because they are simply, honestly, the most massive things around, and mass defines gravity, and gravity defines structure. and structure defines everything that we call a galaxy, a solar system, a planet, a life. We asked what sits at the center of the Milky Way. The answer is an ancient, spinning, nearly lightless object of incomprehensible density, surrounded by some of the most extreme conditions in the known universe, wearing the ghost structures of its last great exhalation like the rings of a very old, very slow breath. But the deeper answer, the one the journey toward it reveals, is that the center was never really the point. The point is the relationship, the orbit, the 4.5 billion-year dance between a small, warm, rocky planet and the dark anchor that holds its galaxy together. You are not at the center, neither is SGRA, but you are both in the only sense that matters, exactly where you are supposed to be. Here is the question I want to leave you with, and I genuinely mean this. If the universe has no center, and every observer stands simultaneously at the middle of everything they can see, does that make you feel more connected to the cosmos, more intimately threaded into its structure, or does it make you feel more alone? There is no right answer. Both responses are honest. I would love to know which one rises in you. Leave it in the comments. Let us go back to the beginning, just for a moment. Not to repeat what we have already covered, but to feel the full distance we have traveled. At the start of tonight, you held an image. A flat, elegant spiral, glowing softly at its center, familiar and comfortable and quietly confident in the way that images absorbed in childhood always are. It asked nothing of you. It offered a simple, satisfying answer to a question you may not even have known you were carrying. It said, "This is what our galaxy looks like. This is where you live. This is the shape of home." And for most of us, for most of our lives, that was enough. It is not enough anymore. Not because the image was a lie, but because the universe turns out to be so much more extraordinary than any lie it might have told. What we found behind the dust wall, behind the curtain of molecular gas that has hidden the galactic center from every human eye since the first human eye opened, was not a brighter version of the familiar. It was something of an entirely different category. Something that bends the language of description almost past its limits, that requires a new vocabulary borrowed from the edge cases of physics, that sits in the sky not as a glowing warmth but as an ancient, spinning darkness, felt only through the motion of the things surrounding it. We traced those motions. We followed the orbit of S2, a star traveling at 17 million miles per hour, completing its loop in 16 years, confirming through the slow rotation of its ellipse that the general theory of relativity is not just a mathematical abstraction, but a living, observable fact written into the fabric of the galactic center. We discovered S4716, orbiting in just 4 years, sweeping through conditions that would vaporize a human being before they had time to register what was happening. We watched, through decades of patient infrared observation, as dozens of stars mapped out the invisible architecture of something 297 million times the mass of our Sun. We gave it a name, Sagittarius A star. A name with an asterisk, borrowed from the notation for excitement, for heightened state, for something more than ordinary. And we looked at it, directly. For the first time in history in May 2022, using a telescope the size of the entire Earth assembled from 8 observatories on 4 continents. We produced an image of its shadow, the absence of light at the center of a glowing ring of superheated plasma. The silhouette of an event, horizon 270 light-years, away, smaller than the orbit of Mercury, heavier than 4 million suns. We looked at the center of our galaxy and saw a darkness shaped like everything we had always hoped to find there, and it was, in its own way, perfect. We explored the neighborhood. We found young stars that should not exist by any model we currently trust. Burning hot and blue in a region where birth should be impossible, their presence. A reminder that the universe is under no obligation to obey our theories, that nature is always a step ahead of the frameworks we build to describe it. We found G2, the cloud with a hidden star inside, surviving its closest approach to the event horizon intact when the models predicted destruction. We found D9, a binary star system, two stars orbiting each other while orbiting the black hole, defying the tidal forces that should have separated them long ago, a small, improbable family living in the most extreme neighborhood in the galaxy. We found organic molecules drifting in Sagittarius B2, glycolaldehyde and precursors to amino acids, the chemical ingredients of life spread cold and patient through a molecular cloud 3 million solar masses wide, 300 light-years from an event horizon, waiting for conditions that may or may not ever arrive. We pulled back and found the Fermi bubbles, two enormous lobes of gamma-ray energy 25 light-years tall, each rising above and below the galactic disk, inflated by an event so energetic it required the equivalent of 100 billion supernova explosions. Created perhaps 3 million years ago when SGR-A was not the dormant, barely breathing object we observe today, but something far more active, something blazing, something that our ancestors walking upright across the African savanna may have slept beneath unknowingly on nights when the sky above them was brighter in frequencies they could not detect than anything our civilization has since produced. We found that the galaxy we thought we lived in, the quiet spiral, the settled, mature, orderly structure, is in fact the dormant phase of something that breathes on million-year timescales. We found that its breath is still in the air. We found that it stirred again just 200 years ago, that the X-ray echoes of that stirring are still traveling through the surrounding clouds, that the sleeping giant is not entirely still. And then we pulled back one final time and found something that no diagram had ever shown us, because no diagram can show it easily. We found that the concept of center itself, the very word around which tonight's entire journey was built, is a human construction overlaid on a universe that was not built with human convenience in mind. The universe is not organized around any single point. It is not arranged concentrically outward from any privileged location. Every center is local. Every center is gravitational. Every center is the product of particular initial conditions and particular histories of accumulation that could, in principle, have been different and would have produced a center elsewhere. The center of the Milky Way is not a cosmic fact. It is a consequence, an ancient consequence, billions of years in the making, built from mergers and accretion and the slow, inexorable arithmetic of gravity working across time. It is where mass accumulated. It is where the math said something heavy would form, and something heavy formed there, and the galaxy organized itself around it, and our sun fell into its long orbit around it 6 billion years ago, and the orbit continues tonight, right now, at this very moment, as it always has, as it always will for billions of years to come. The question we asked at the beginning of tonight was the right question. Not because it had a simple answer, but because in following it all the way to the end, in refusing to stop at the comfortable image, in pushing through every layer until the original frame itself dissolved, we arrived somewhere true, not at a center, but at an understanding of why centers form, what they mean, what they contain, and what they do not. What sits at the center of the Milky Way is an ancient, spinning, nearly lightless singularity of collapsed spacetime, 297 million times the mass of the Sun currently sleeping, occasionally flickering, surrounded by one of the most extreme and paradoxical environments the universe has yet produced, wearing its past violence in the form of enormous ghostly lobes above and below the galaxy's disk, waiting with the patience that only something truly old can muster for the next meal, the next awakening, the next slow exhalation, and it is 26,000 light-years away, which means it is, in the only terms relevant to the life you are living, extraordinarily far. It exerts no meaningful pull on you beyond the grand, slow, shared orbital motion that carries the entire solar system gently around it on a path 225 million years long. It has never threatened you. It will not threaten you. It is your galaxy's anchor, not your enemy. It holds the structure that holds the stars, that hold the planets, that hold the oceans, that hold the chemistry that eventually, improbably, beautifully, produced the carbon and the water and the electrical gradients inside a nervous system that is, right now, comprehending all of this. You are a small, warm, conscious arrangement of atoms living on a rocky planet orbiting an ordinary star in an outer arm of a barred spiral galaxy, 20 orbits out from an event horizon that has been there since before you existed in any form, and will be there long after every trace of you is gone, and you spent tonight looking at it, not with telescopes, not with mathematics, but with the one instrument that makes any of this matter at all: the mind that wants to know. That cannot look at the night sky without asking what is out there, that refuses to accept the comfortable diagram when the real thing is stranger and deeper and more worthy of attention. That impulse, the one that brought you here tonight, to a long, slow, patient journey toward the center of the galaxy you live inside, is not a small thing. It is, arguably, the most remarkable thing this universe has yet produced. Everything else we described tonight, the black hole, the S-stars, the Fermi bubbles, the molecular chemistry, the galactic merger still 4 billion years away, all of it exists without knowing it exists. Only you know. Only we know. Only the peculiar arrangement of matter that produces consciousness and curiosity, and the capacity to be genuinely moved by the scale of things, looks up at the galaxy and thinks, what is at the center of that? What is the name of the dark thing at the heart of everything I live inside? What am I orbiting? And the answer comes back from 26,000 light-years away, in the infrared glow of superheated plasma, and the echo of X-rays still bouncing through cold gas, and the careful mathematics of a star completing its 16-year orbit. The answer is something ancient and something quiet and something that was here long before you and will be here long after, holding the galaxy together without effort, without intention, by the simple, overwhelming fact of its mass. You are orbiting it tonight. You were orbiting it last night. You will orbit it tomorrow and next year, and for all the years available to you, and long after you, in a galaxy that will still be turning, still organized around its dark central anchor, long after the name of our species has dissolved into silence. If you found tonight's journey worthwhile, if this kind of deep, slow, patient exploration is something you want more of, a like and a subscribe help this channel continue making exactly this kind of content. It genuinely matters, and it takes only a moment. I am grateful you stayed for all of it. Now close your eyes if they are not already closed. You are on a planet. The planet is spinning. The spinning planet orbits a star. The star orbits a galaxy. The galaxy turns slowly around a dark ancient spinning point of collapsed spacetime 26,0 light-years from here, invisible to the naked eye, named for the constellation of the Archer, which rises in the southern summer sky and sets before midnight, and under which on any clear night, if you know where to look, you can stand in the dark and point at the exact patch of sky where something 4 million times the mass of our sun sits in silence, and has always sat in silence, patient and enormous and utterly indifferent to whether or not we ever found it. We found it. Sleep well, good night.